right. Hey, everybody. Welcome to... Ooh, turn this down a bit. Hello, everybody, and welcome to the Astro Coffee Hangout. I'm adjusting my volume as I talk. I'm Tony Darnell from deepastronomy.space, and you are back to Astro Coffee Hangout, 3 o'clock on Thursday. My guest today is Dr. Brian Keating. He's a professor of physics at the University of California at San Diego. He's also the author of the book Losing the Nobel Prize, which... I guess you lost it. Is that right, Brian? Is that right?
Yeah, well, arguably I was in the running for it. It's actually a double entendre, as our French friends would say. It's sort of the story of how I came very close to arguably being selected for it. In fact, being asked to nominate the winners of the Nobel Prize in 2016, and then coming up with ideas for reformation and rebirth of the prize, and losing it in the colloquial sense, getting rid of it in its current form and revitalizing it in a way that's representative of how science is done today, not in 1901.
Right. Well, we're going to get to that in just a little bit, but I just spiked everybody's eardrums because what you're hearing and what I'm streaming are two different things. So you should be better now. Yes. Okay. Sorry about that. All right. So we're going to get more to his book, but before we get started, a couple things I want to let you guys know. We're live on YouTube. I'm definitely looking at the chat here. Adam Synergy and John. I'm so good to see you guys again. It's really good to have you back in the fold. And we are also going to part of the reason that Brian's joining us here is he wants to also promote his YouTube channel. Now, you can go to his YouTube channel. The link to it is in the description box. There's also a link to his book as well if you want to check it out. But Brian, you want to promote your channel a bit? You said you had some stuff for people.
Oh yeah. So I have a piece of the villain of my book. You know, most books that have villains, you can't actually give away the villain of, I don't know, what's my favorite movie? 50 Shades of Grey. No, that's not my favorite. But
really?
It's a good movie. I'll say, actually, I watched Return of the Jedi last night on the flight home from Princeton University, and Darth Vader, somebody like that. Okay, so you can't include him in a book about that, but you can include a piece of meteorite. So this is a meteorite that fell in Argentina, they think in about 1500s, in a place called the Campo de Cielo, the field of the sky. And this meteorite is 4.3 billion years old. I've actually done chemical assays of it using X-ray spectroscopy, provided by one of my friends and followers on Twitter, Brian Field, who's a professor in Long Island. And Brian and his colleagues did an X-ray spectroscopic survey of this sample, the same meteorite that I have here. So I'm going to give away 10 of these meteorites to the first 10 people who sign up for my mailing list using last name Deep. So you put last name is Deep, and if you live in the U.S., I can send you one of these. Unfortunately, although gravity brought this to Argentina, the U.S. Post Office won't let me send these from UCSD to any other foreign countries, unfortunately. So sign up for my mailing list on my YouTube channel. When you sign up for my mailing list, use last name Deep, and I will send this to you. As I did last time on the call, I got almost a dozen people that did this, and I sent them meteorites too. So I hope people like it. I hope they see dust for the villain that it is, but also the kind of dual nature of what dust can do for life on Earth as well.
Okay, well, so tell us about your channel. What kind of content do you post? What can people look forward to when they subscribe?
So I have a very diverse podcast repertoire in terms of the guests that I have. I usually have guests that are outstanding authors or achievers in certain fields. So the most recent 5 or 10 episodes have been Sean Carroll, everybody's favorite quantum mechanic, Sean Carroll. I had on Richard Panik, who wrote the book called The Trouble with Gravity. I had on Jim Gates, Ford Foundation professor at Brown University, my alma mater. And he and I talked about his new book, which is called Proving Einstein Right. And last but certainly not least, most recently, was Dr. Jessica Meir, who is on the space station right now. And she gave a phenomenal interview, and I was really treated and honored to have the chance to speak with her in the most expensive call I've ever made, the most expensive podcast ever. It puts your awesome production values to shame. I have to say, communicating with the space station is the highest honor, and maybe someday I'll hook you up with her when she's back.
Oh boy, well, yes, that's that's talking about hanging out with the cool kids. So,
and I just got a invitation accepted by Peter Diamandis to come on my show. So we get great authors, experts. I had on Paul Davies last week, who who wrote The Eerie Silence. We talked about why hasn't ET phoned home, and I sort of entitled that episode, Why Is There Nothing Instead of Something, which is kind of the opposite of his former colleague at Arizona State University. Lawrence Krauss wrote a book, A Universe from Nothing.
Right.
And this kind of questioned the notion of, if life is so ubiquitous, how come we haven't heard anything? In fact, how come the silence is deafening? So there's about 50 or so videos that I've been on, and I cover all different topics. I've even had on a woman who wrote a phenomenal book about achievement by female venture capitalists that seeded Silicon Valley. Julianne Guthrie, she's a good friend of mine. So I have on a mixture of people that are at the highest level, usually in science, but sometimes outside of science.
Wow, man, that's quite a list, man. I didn't realize you were that you were also just that you were talking about Paul Davies.
Sign up.
I mean, I know Sean Carroll, big fan. So so definitely subscribe. And this is all done. You're doing all this on your YouTube channel, right?
Yeah, doing this all. Yeah, it's part of the Arthur C. Clarke Center for Human Imagination, which I co-direct here at UC San Diego.
Great. All right. Well, so definitely check it out. Links in the description box. Brian, thank you for taking time to talk with us today about all kinds of stuff. But the big thing I want, and I talked to you about this before we got started, the big thing I want to go into here is the early universe. Now, we've had a lot of hangouts. I've made a lot of videos. We've talked a lot about the Big Bang and the large scale structure of the universe. But I want to dive into the very early moments specifically of the Big Bang. So for those people who are watching that maybe don't have as much of a knowledge as I'm saying that a lot of my audience has, let's just sort of set the stage so all of us is on the same page here. And I'm going to put up, I don't know, one of these graphics, probably entire universe.jpg or something while you're talking, and you can maybe set the stage for what we know about the universe as a whole, and why do we go back in time, and can we go to a singularity, and all that, just the basic cosmology spiel, and then we'll go into some specific questions I have.
Yeah, so I'm sure most of your listeners and viewers are familiar with the fact that light travels at a finite speed. And it doesn't matter if it's visible light, infrared, heat, or radio waves. And in fact, when you look out in space, you're looking back in time. So when you look out in space, you're seeing something, for every foot something is away from you. You see it 1 nanosecond earlier than it is actually right now. So this is due to the consequence that light travels at 300,000 kilometers per second. And so if you do the math, it's about a foot per nanosecond. Or if you remember back in the moon landing, or you've seen videos, it's about a second and a half to travel 250,000 miles to the moon, and then another second and a half to make the round trip. Well, if you look where the moon isn't, and you look where there's no galaxies, stars, or other phenomena, you could be looking back to the earliest possible form of light that ever existed in our universe, at least that's visible today. And that's called the cosmic microwave background radiation. We call it microwaves because in 1965, Penzias and Wilson, working at Bell Labs in Holmdel, New Jersey, where I went last November for the first time, that telescope discovered serendipitously that there was a persistent hiss, a glow that was emanating all around us, a background of heat that was later found to be consistent with a very hot early evolution of the universe, which itself was commensurate with the formation of the nuclei. And we'll get into that in a bit. But what that means is what we call the Big Bang is really, what we mean by that is the formation of the lightest elements on the periodic table of the elements. And so by virtue of the fact that light travels at a finite speed, and microwaves too, just another form of electromagnetic radiation, we are able to peer back in time. You know, astronomers have only about a couple of things that we actually can do experiments on. One are actually these meteorites. I told you my friend Brian Field, Professor Field, he did experiment on this chunk of rock. Well, it turns out that this is one of the few things that astronomers ever get to play around with in the lab and do experiments on. In other words, most stuff that we study comes only in the form of light as astronomers. And furthermore, we can't do a proper experiment. I can't change the temperature of the sun and see how does that affect the habitable zone of possible life forms in our solar system. So by virtue of the fact light travels at a finite speed, when we look out in space, we're looking back in time.
Okay, and so, while you were talking, I put up various representations that we're all used to seeing of these different things, and so embedded in this, of course, is the idea that the universe is expanding and that it's accelerating as it does so. And so by running this clock back, not only are we looking back in time, if we look at a distant galaxy from Hubble, let's say, that has a high redshift, and one thing I'd like to, is there an easy way to go from, saying redshift to using the number Z? Like, can you say Z equals 2 and have some idea of how far back in the universe you're looking at?
Yeah. So when we say Z equals 1, that's the easiest one to associate with. Z equals 0, by the way, is today, is current size scale of the universe. So Z, this redshift factor, represents how much has the universe changed in size compared to what it is today. So if you look to where the universe was half as big as it is now, we call that redshift of 1. So we would say we add that redshift, it's doubled in size since a redshift of 1. So the size difference of the universe is 1 plus Z. So today, compared in a ratio to when the universe was 7 billion years old, roughly, it's actually slightly different because time and spatial expansion don't linearly relate, but we can correct for that. Roughly speaking, when the universe was half its current size scale, when it was half as big as it is now, when everything, all the distant galaxies were twice as close as they are now, they've expanded away since then. The universe had a redshift. We're looking at objects at a redshift of 1.
And so when we look at these distant high Z galaxies from way back then, we are looking at the light that has traveled, say, roughly 13 or 12 billion years, whatever. I think the most distant was seen by Hubble was something like 11, and they saw 11 billion light years away. And it was,
that's right,
when the universe was, I forget, like just a few billion years old, but it needed gravitational lensing to help it see it because it was so far away. Hubble wouldn't have seen it with its own optics and objective diameter. So
exactly.
when we look way far back, we're looking at old galaxies. These galaxies are funky looking. They're big blobs. They're very irregular looking. But this is a time representative when the universe, if it's expanding and getting bigger now, if we go backward, then it must, logic says, be getting smaller. And so cosmologists turn the clock back. They crank the clock backwards, trying to run a reverse movie of the universe. And we've gotten pretty good at doing that, right, Brian? I mean, people are pretty confident about what the history of the universe is from, say, the time of the cosmic microwave background. I mean, from that point forward, we're pretty confident, right?
Yeah, so here's the way I like to think about it, and this is courtesy of our mutual friend, Sean Carroll. What Sean says, and I think it's an important distinction, when the universe produced its first elements, the first element synthesis of the nuclei of hydrogen, not the hydrogen atom, not an electron and a proton, but just a proton. When it fused a proton and 2 neutrons together, say to make helium, that event is called Big Bang nucleosynthesis. Long after that time, hydrogen was able to form in its molecular or atomic state, rather, where it acquired a single electron. When that occurred, the universe became transparent to electromagnetic radiation. That took 382,000 years. So the process from when the hydrogen was present by itself and forming helium till the universe cooled enough to form atomic hydrogen, that took 380,000 years. The time that it took to fuse the 2 protons together was about 20 minutes. So all the nuclear reactions that produced helium, lithium, little beryllium, and other of the light isotopes of those. So tritium is a heavy version of hydrogen. All those were produced in a shorter time period than the Big Bang Theory TV show. So all the light elements, which then became the fuel to produce the stars that would later fuse more of the hydrogen into helium and then helium into heavier elements, eventually becoming supernovae, etc. That process took place in what we call the first 3 minutes, perhaps as long as 20 minutes. So shorter, again, than a sitcom series named after the theory. Now, when that occurred, that sort of marks the end of our knowledge or the beginning of our ignorance. If you're going backwards in time, we really don't know because we don't have examples of things at energy scales much higher than the energy of nuclear fusion. Fusion is much more energetic than fission, and we don't have many examples of processes like nuclear fusion, but are much more energetic. So we don't actually know what happened much before those first 3 minutes. In other words, we don't know what happened at time equals 0. So what Sean says is that looking from today back to the formation of the elements. That's the Big Bang. That's the expansion. That's the evolution of elements into heavier elements. But it's also the end of what we say could be known physics based on what we know today, and into the realm of ignorance and perhaps speculation as to what came before. So you shouldn't hear Big Bang and think origin of time. You should really think origin of matter. And that's equally impressive, right? People think, oh, it's only important if you create just the time itself or the universe began. We don't know if the universe began at what we're considering to be the time equals zero, right? It could be. I was in Princeton University yesterday, as I said, meeting with my good friend Paul Steinhardt, who would be a great guest someday for you as well. And he's been on my podcast. He's written many books. One of them is called Endless Universes. And it's about how the universe could be cyclically complete. In other words, our universe, the raw material that became our universe, could have emerged from a previous universe without any singularity, without any beginning of time, if you will. And so it's not tantamount. The Big Bang is not tantamount to the beginning of time. It could be. We just don't know.
Now this is okay. We're getting there. We're getting where I want to go, because this to me is. I feel like I've been thinking about this in ways that were either inaccurate or just maybe needed. They weren't quite reflecting the latest ways we're thinking about this. So the time you're talking about, this time when the first atoms, the hydrogen atoms were created, fused into helium, and all of this stuff. This is way before the wall that we see as the cosmic microwave background, right? You're talking the first 3 minutes. The furthest back our telescopes can see is about 380,000 years later.
Correct.
Right?
Absolutely correct.
Okay.
With telescopes that see light. The key is
that see radiation. Let's say radiation.
Electromagnetic radiation. Because gravitational radiation you could see.
Because Avi Loeb says, and you tell me if I'm saying this correctly. I was reading it in a paper he wrote, that you can actually see a little bit further in if you use radio, and you could radio detectors or radio telescopes. You could see behind the CMB at the 21 centimeter line, I think. And is that right? We could maybe see just a little bit further back than the 380,000.
I wonder if that's what he means. I haven't seen that. Avi's incredibly creative intellect. I have not seen that.
Somebody's been through the Oumuamua thing, right?
That's right. Yes. So he is not without his controversies. But
right,
that's okay.
I know.
Yeah. So that would be hard to believe, because that signal from the formation of hydrogen, it might be maybe thousands of years, but the duration at which it took hydrogen to go from a plasma of ions of protons and ions of electrons to then form atomic hydrogen, a proton plus a neutron, a proton plus an electron bound together. That time scale was maybe 10,000 years or
okay, so we're not going.
At most you could go to. No. But with gravity waves, with waves of gravitational radiation, you could theoretically go back not just to 1 year after the Big Bang, not just to 1 day after the Big Bang, but or the origin of the universe. Sorry, I shouldn't say Big Bang, but not just 1 day after the origin of time and space itself, but perhaps 1/trillionth of a trillionth of a trillionth of a second after the origin of time in our observable universe.
Okay, I want to take a brief pause right here because we're getting some good questions, and I'm going to go ahead and read them out because I want to go behind. I want to go back to the first 3 minutes because I'm about to get to the meat of some of the things I want to learn. Mitzvah Golem, great handle, by the way.
I love that.
What made quarks and electrons?
So if I told you this, Mitzvah Golem, then I think I could say, it was made up of, let's say I say it was made up of clay, like a golem. Okay. So and then you could ask, well, what made the clay? Right. So there's sort of this infinite regress, which is delightful in a way, but the answer is it was made predominantly from the formation of energetic photons. So there was heat, there was radiation. Now you're going to ask me, Mitzvah Golem, I'm waiting. What's taking you so long? You're a smart guy or girl. I don't know. That you're going to ask me, where did that come from? So the answer is, again, we don't know. If there was light, if there was energy, it is certainly sufficient via a process called pair production, that one can make pairs of particles, matter and antimatter, that come in these different flavors, some of which could be positrons and electrons, some could be neutrinos and antineutrinos, and other forms could be quarks and antiquarks of all different flavors. And in fact, what is said in physics often is that which is not forbidden is mandatory. In other words, if a process is not prevented from occurring due to the laws of mathematical symmetries or violations of the laws of physics, it must happen. In fact, it must happen perhaps an infinite amount of time, or near infinite amount of time. In the case of the formation of protons and molecules, et cetera, eventually we have 10 to the 80th or something protons in the observable universe. So a huge number, far beyond the notion of human comprehension. But you can always ask the question, what created the light that created these anti-quarks and quarks via pair production? And that we simply don't know right now. There are theories, one of which is inflation.
I never heard of that before. So if it can happen, it must happen.
Yeah.
Wow.
So if you have a wall and you throw a baseball at it, theoretically, if you take an electron and you throw it at a wall, an electron's just a small baseball in this context, it'll bounce off the wall. It'll never get through. But because of a process called quantum tunneling, there's a finite probability. It's suppressed very heavily. It might be an exponent with a negative power, so e to the minus 1,000 or something like that. But that means like there's still a chance. And I was watching, as I told you, Return of the Jedi, and the previous movie, it's called The Empire Strikes Back. C-3PO tells Han Solo, so I binge watch it. My kids.
Well,
and Han Solo says, C-3PO says, there's no chance of getting through an asteroid belt with this density. There's no chance at all. And Han says, never tell me the odds. I'm like, come on. You can't say that. He's not a physicist. The odds, if they're greater than zero, you got a chance, in the words of George Costanza.
Okay, great. Well, let's get this question out of the way because we're still talking about things that we're pretty familiar with at this point. God, I must be living in some kind of special astronomy bubble to say that, because here we are talking about large scale. Well, we know all this by now. Let's just get this out of the way. But Neil Yu wants to know, and this is a common question, so let's get this one out there. How much bigger is the universe than the visible horizon by volume? So maybe explain the difference between the observable universe and the entire universe and that kind of thing.
Yeah, so it actually turns out that the universe, what we can theoretically observe, is, as I said, using light, you can go back 13.8 billion years to when the formation of the elements took place. Theoretically, you can go back, add 300,000 years to that number, but that's pretty small. You basically say 14 billion years. But yet the universe's diameter is more than the speed of light times 14 billion years. In other words, that would be 28 billion light years. It turns out the real number is about 3 times that amount. In other words, there's 3 times more space than just the speed of light times the age of the universe. And it's for a simple fact. The universe has expanded since that time, and it's expanded at a much faster rate at different times in its early evolution, such that you don't have a linear relationship between time and distance by this multiplicative factor. You have to solve what are called the Friedmann equations, and if you do, they depend on the amount of matter and energy in the universe, and they evolve over time. Eventually, they give you an output called the Hubble parameter. You may have heard of the Hubble constant. It's extremely controversial, and we can get into that.
I do, but I think I want to do that in another hangout. And this one I want.
We'll do that in another. Yeah, let's do that, because that is actually something we can shed light on, no pun intended, with technologies from the cosmic microwave background, combined with our friend and yours at Space Telescope, Adam Rees.
Right.
And we can combine these measurements and perhaps reveal a deep mystery. Let's talk about that next hangout.
We'll do that, because the whole Hubble law thing is interesting in and of itself.
It's so fascinating. But the output of the Friedmann equations, they tell you not only what the Hubble constant should be, but also that the size of the observable universe from which we can get information from the CMB. It means that the CMB, the surface of last scattering, the photons that are just reaching our telescope now, they have traversed about 46 billion light years, not 14 billion, 46 billion. So it's 3 times larger than you would expect.
And that's because the expansion rate of the universe isn't bound by the speed of light limit.
That's right.
Yeah,
that's right. It's like an ant walking on a ball, as if the ball's expanding, is going to walk further in terms of its proper distance compared to the coordinate system in which it's embedded. It will walk farther, even though it doesn't feel like it walked farther. It walked, the speed that it's walking times the time that it walked, so 14 billion years. But space itself is expanding. It will move a greater proper distance.
Right. Okay. So Mitzvah Golem, let me just comment and read his comment. Infrared that is not visible will be measured by JWST earlier than 15 billion years ago. I think that's a question, actually.
No,
Yeah.
it won't. It can only measure things that, since the production of electromagnetic radiation, what JWST is particularly appropriate for is the measurement of the dusty kind of early universe, that when the production of light from the first galaxies and first structures. It won't see heat, any electromagnetic radiation from before the surface of last scattering that produces the CMB.
Yeah, and I just want to say that the infrared radiation is what that will allow JWST to see is the very first stars and the very first galaxies to ever shine. But that's pretty much where it's going to be at its limit. Andrew Planet, just want to give him a shout out. The universe, if the universe is 13 billion something years old, does that temporal ascribing mean it's finite but pretty big?
No, it doesn't mean that it's finite. In fact, we don't know. Again, see, the problem is most cosmologists, and I'll include myself too, we are uncomfortable, very deeply so, saying the following three words: I don't know. And when we say that, we feel like someone's going to feel like,
I should know.
Yeah, you should know everything. You're like a walking Wikipedia, right? What good are you? Because, it's debatable what else we do in society. But nevertheless, let's leave that aside. If you consider that the universe is has this expansion and is getting bigger over time, the natural question is expanding into what? Now that is a whole other coffee chat. Okay, the question of what are we expanding into? Yeah. Again, I don't know. Right. However, the material, like what it's expanding into, presupposes there's some greater boundary, there's some greater volume surrounding what we can see with our eyes. Like, you think that there's a room behind this room over here, but you don't know for sure that there is. How could you get evidence that there's something in there? Well, it's not like we're expanding into, the atmosphere of the Earth is getting bigger, but and going into space. But actually, what space could be expanding, what our universe could be expanding into, is actually very simple to describe. And I don't know if you've ever heard this, and I'll try this on you, Tony, and your listeners can tell. Go into the International Space Station, go 10 feet outside of where I interviewed Jessica Meir a couple weeks ago. And she goes out there without her spacesuit. Of course, she'd die. And she was part of the first all-female spacewalk in human history.
Right.
Pretty amazing.
Yeah.
And she's also an alumnus of UC San Diego and Brown University alumna. And so we have a lot of affinities, but that's where the similarities end. Now, because she's much more brave than I am. If you go outside that spacesuit of hers, you're in space. You're not in like deep interstellar space, but you're in space, right? Now go out there and make a box, and that box, make it 1 centimeter on a side, a cube 1 centimeter on a side. What do you think is in that box? Is there anything in it? Is it completely empty? Tony, I'm asking you.
Completely empty.
Yeah, we're near the sun, we're near the Earth. I mean, could it be completely devoid of anything?
Oh no, sorry. Yeah. Sorry, there'll be molecules in there of something.
There'll be molecules. Right. It's a high vacuum. Right. It's not the infinite vacuum. It's a high vacuum. I'll tell you one thing. The most of what you'll find in there are photons. You'll find exactly 419. Sorry to disappoint people out. They always want it to be 420, but I'm not going to say 420. It's 419 photons from the CMB per cubic centimeter. Yeah, dude, let's not get that deep. Okay, so if you have a cubic centimeter, you're trapping within that box 420 photons from the Big Bang, okay, from the origin of the elements on the periodic table. That's leftover heat. What's between those photons? Pretty much nothing. There might be some neutrinos in there. In fact, there'll be 100 or so neutrinos inside that box too. And what's between those? Nothing. You might get one molecule of the Earth's atmosphere, but most of the box will be basically empty, right? It's not going to be like a sugar cube. It's going to be mostly empty. You have a volume the size of a sugar cube. It has a lot of photons that you can't detect, has a lot of neutrinos that we don't really interact with, and it has maybe 1 or 2 protons in that whole box, better than any vacuum ever. Now, what is between those protons or those photons? Nothing. Absolutely nothing. And that's exactly what you can think about us expanding into, should there be a finite region or an infinite region that surrounds us. We just don't know where that infinite region, that space, the points in space and time, where do those come from? We don't know.
Yeah, you caught me reading the chat when I answered that, so I was.
Sorry.
Just basically.
No, I know you. I know you know the photons.
Yeah. So, okay. So, and that also is another great topic for a hangout. What is nothing? Because the answer is very non-trivial. To have absolutely nothing, and is nothing even possible? So that's another big conversation to have. So the problem, of course, always comes down to our biology. I think imagining what we're expanding into. is a very difficult thing. We have these things of something expanding into something else, and not something expanding into nothing. And so that's a very difficult thing to think about. When you actually think about what nothing is, it becomes a very difficult mind problem or thought experiment, in my opinion. So
absolutely. That is a huge topic in and of itself.
In and of itself. So I want to read one more question, and then I want to get because this will sort of sum up this section of our discussion. And that was from Hans Milling, who's asking, again, this is about the large scale structure of the universe and expanding universe. He's asking, is the distance between all molecules expanding even inside us, or the empty space between matter?
So it turns out So despite, what I'd like to blame my, recent weight change on, it's not anything to do with the expansion of the universe. For example, things that are attached by chemical forces are not expanding. Our solar system isn't even expanding. The expansion is operating on the scale of galaxies, clusters of galaxies. Huge, vast volumes of space and time are getting farther apart. For example, even us and the Milky Way galaxy here that we're a part of, and the Andromeda galaxy, we're actually coming closer together. So if Hubble only looked at the Andromeda galaxy, his conclusion would have been very different. It would have been, the universe is getting smaller, and that would have made a lot of sense, because things that have matter, if you throw a baseball up on Earth, you expect it to come back down. And so anything that has gravity, anything with matter has gravity, and that gravitational force should slow the universe down, should cause everything to be coming together if it's dynamical at all. In fact, he found the opposite, it was expanding. And that can only happen using certain kinds of the solution as a solution to, again, this Friedmann equation, out of which comes the Hubble constant and other things. So this equation tells you when you have energy, things expand, but it's a gravitational expansion. It's not on the scale of molecules, atoms, or my waistline, unfortunately.
Yeah, I think the thing I've always heard was that if things that are gravitationally bound aren't affected by this, it's the
or chemically bound,
chemically bound,
or nuclear,
it's the large scale structure of the universe. The universe as a whole.
Only things that are unbound by gravity. So clusters of galaxies that are in what's called the Hubble Flow. After you get outside of a few megaparsecs, a few million light years away from the Milky Way galaxy, then every galaxy you see is expanding away from us. Within that Hubble volume, within that region of spacetime, like Andromeda is the closest major spiral galaxy, within a couple of megaparsecs, things are getting closer to us or orbiting around us, like the Magellanic Clouds that your listeners on the southern hemisphere can see on a given night. So things that are close are gravitationally bound to us. They might orbit us like we orbit the sun. But anything much beyond the orbit of the distance of Andromeda, is all of those are expanding away. So you have to ask the question, what makes us so special? Why is everything expanding away from us? Well, it's not. Everything's expanding away from everything else.
That's right. No matter where you
go to Andromeda, you'll see the Milky Way coming towards you and everything else expanding away from it. That's why we can't say we're the center of some explosion. And that's why that's not the right way to think about what the Big Bang actually was.
Right. And that's what comes from the nomenclature. I think Fred Hoyle did us a disservice by starting with that Big Bang term. But anyway, okay, so there you go, folks. There's kind of a 70,000 foot altitude look at the history of the universe up to about the Big Bang, or the cosmic microwave background horizon that we can visually see. And Brian, you were talking earlier about this point up to the first 3 minutes. Now, this seems to me is where the frontier of cosmology resides, is in trying to answer a lot of these early questions within, say, the first 3 minutes of creation.
Yeah.
So what you said earlier in the hangout was that we can think of the Big Bang as a time when, not a t equals 0 time necessarily, but a time when matter was created.
Mm-hmm.
This is where
that's right. The ordinary matter of which we're made was created. That's right.
And prior to this, we had this period where the universe was in this state of expansion that was so great. It was exponential in nature. It didn't last very long, but the energy that came from that inflationary period is what was converted into the matter that please correct anything I'm saying that's wrong. That inflationary energy was created or was converted into the matter that made the universe that we now see. And it didn't necessarily. Time is very confusing during here, because we've got a universe in the span of just moments getting exponentially huge, with a lot of energy, and then matter is created. Can you help us maybe get a sense of what that period in the universe was like? And was it actually the Big Bang? The Big Bang, if what you're saying is true, it's the creation of matter, then there was a period before then where there was no matter, but there was all energy.
Right. So these are all fascinating questions, and I'm so glad we can talk about them. When I describe this in my book, I talk about losing the Nobel Prize, which I recommend to folks. And
link is in the description.
Money from these books,
definitely
but please,
check it out.
please pick it up, because it does cover these essential existential questions. How did we come to be? What predated the universe? And I have some quotations from folks like Sir Roger Penrose, who was on my channel about a month ago, talking about the 30th anniversary edition of his Titanic work called The Emperor's New Mind, which is about AI and brains and stuff. But he's one of the foremost proponents of what's called a non-inflationary cosmology. So inflation, as I describe in my book, Losing the Nobel Prize, it characterizes something that we've all thought about. Like, I'll ask you, Tony, what's the most important day on the calendar for you and has been your whole life? What's the most important date on the calendar?
Oh boy, I never thought of it. I have several, but I have to pick one.
Pick one. Yeah, pick one. What day of the year?
I guess my birthday. I'll say that.
Yeah, your birthday, of course. Most people say that. Or they'll say New Year's Day or Christmas or whatever, right? So why is that? Because that's when you originated. That's your origin story. That's when you became an entity on this planet in this universe. So that's why it's so natural for every human being to wonder, what was it like on the universe's birthday? And if indeed the universe had a birthday, if it was created, if you're religious, if it came into being, if you're not, it doesn't matter either way. We have a natural desire as human beings that makes us uncomfortable when we don't understand how something began. That's why I always point out, that's why the Bible, which is about like laws and place in the Middle East that very few people have been to, it starts with the Big Bang, or it starts with the origin of the universe. It's that let there be light. And I'm not using this to promote anything religiously. I'm just saying that shows you, and that's the best best-selling book of all time, right? I always say I'd kill for 1% of God's sales, but I'll settle for what I can get. Now, the origin of that shows you why it's so deep within the human being's psyche to want to understand origin stories. And in our case, we have come up with many different explanations for the very puzzling fact that everything is moving away from us, that we've known since 1929, since Hubble really took advantage of work done by Henrietta Leavitt and Vesto Slipher and other people to show that the universe is expanding. That meant it's not static, as had been thought for 2,000 years, including by Einstein, that the universe is static. In fact, he put in the cosmological constant. He called it his blunder. His greatest blunder. Those were meant to keep the universe static because it didn't seem possible that a universe with matter, look, I have this meteorite that I'm going to give away to people in the US, as I said, who sign up for my newsletter or my mailing list and my YouTube channel. This meteorite falls because of gravity, because the Earth is massive and attracts it. Well, Einstein knew the Earth existed. He knew that the universe couldn't be anything other than contracting unless there was some repulsive force keeping it at bay, because the equations told him that things that go up have to come down, and essentially there was no way to prevent this from happening without this famous cosmological constant. Now, why is that relevant? Well, because once you say the universe is changing and it's getting bigger with time, the natural supposition, induction, is to say, well, what would it have been like in the future? What will it be like in the future? And what was it like in the past? And in that case, it led to the starting conclusion that everything in the universe, all the stars, gas, planets, and so forth, must have been in a form of matter. And that matter must have been, at some point, these galaxies must have been touching. And if you go back even further in time, there must have been a point in which there was all the matter. If you just naively extrapolate the observations, all the matter was compressed into an infinitesimal amount of space. And that leads to mind-boggling, perplexing, conclusions. That you get things called singularities. You get things that have infinite density. And physics equations don't like infinities. They don't play well. They don't adjust well mathematically. And so we had to come up with an explanation of where the energy and matter came from. And the hypothesis was, for a long time, that the universe could be cyclic. In fact, when Penzias and Wilson discovered the Big Bang, the afterglow of the Big Bang, namely the cosmic
CMB,
microwave background, the CMB, they said in their paper, there was a companion paper written by my PhD advisor's PhD advisor, David Wilkinson, and other people like Robert Dickey and Jim Peebles, who won the Nobel Prize this past December. They made a prediction that heat and energy could have come from the collapse of a previous universe. So in other words, they never talk about the Big Bang as being the origin of all of space and time. So, but that was still a big puzzle. Where did the energy come from to convert via pair production? When you smash two high energy photons together, they can pop out of that collision an electron and an anti-electron called a positron, or a quark, an up quark, and an anti-up quark, for example, or a neutrino and an anti-neutrino. All those processes are possible when you have enough energy. In fact, we do it all the time in the LHC. This is a very common process to make pair production from high energy photons. And so, in fact, that production mechanism had to come up with only one thing, one ingredient in the cosmic primordial soup, and that was photons or energy. Where did that come from? That was a huge mystery. And one possibility is that energy came from something mysterious called a quantum field. Quantum fields are very mysterious. They don't behave like any other form of matter or energy that we know about. In fact, they have just the right properties to do the following. They can create space as time evolves. So time has to be present in a sense. The universe has to come into existence for time to progress. And when it does, this field, this quantum field, in this case it's called the inflaton. When the inflaton evolves over time, according to the theory of inflation, then it can actually produce an exponential expansion. The universe can expand by a factor of 10 to the 30th power in size in the short time scale of perhaps a trillionth of a trillionth of a trillionth of a second. That's what the power of inflation. Now, inflation has to end, and we know that if indeed it did take place, because we wouldn't be here. If inflation didn't end and it kept expanding and inflating, the universe would be a fossil ember of nothingness. There'd be no energy left for these photons to have ever encounter one another, let alone produce a photon, because the thing would be expanding away faster than their energy scale will allow them to propagate. In other words, the universe is expanding faster than the speed of light. So you shoot two lasers at each other during inflation, the laser beam photons will never meet, because the universe would be expanding faster. So it had to end. And when it ended, then there was the conditions where these photons could come together and they could create via pair production. And the photons themselves, where do they come from? That's called reheating, which could be another whole podcast. And that's the process by which the energy of this inflaton quantum field sort of becomes a catalyst, if you will, for the production or the raw ingredients for the production of high energy photons. And they are the nucleation points for matter.
Now, what is the general consensus of how long this period of inflation lasted?
We characterize it by the redshift, the amount of redshift that would have been perceived by a photon or the space-time structure itself. That would be an infinitesimal amount of time, perhaps maybe a trillionth of a second, or perhaps a billionth of a trillionth of a second. In other words, we're talking about fractions of the Planck time or multiples of the Planck time.
Okay, so that's what I was going to ask. It's smaller than the Planck time, which is like 10 to the minus 30.
It's larger. It's
larger.
Good. Okay. The Planck time's about
because otherwise we'd never have any hope of.
That's right. Yeah, the Planck time and the Planck distance scale sort of being the shortest quantum of space or time that one could imagine, and they're related by the speed of light.
So there's some multiple. It lasted some multiple of the Planck time.
Correct. About 100 Planck times. So not a very long time at all. And in that case, all the energy that would have been seeded, in fact, all of the fossil relics of that period, including gravitational radiation, which is what I study, that could have been imprinted. And that imprint, that fingerprint of the inflationary process, in theory, should be visible to the telescopes that I build. In fact, we claim detection of that in 2014, just about 6 years ago, on March 17, 2014, we declared, and this is the subject of a good part of my memoir, Losing the Nobel Prize, what that was like to claim and to feel that we had actually witnessed the true origin of the universe.
So Bicep and Bicep 2 were meant to see this signature imprinted on matter of this inflationary period.
That's right. If inflation did take place, it would have produced the photons and the light, but we can't see that light for 380,000 years.
Right.
But the other thing that it would have produced are waves of gravity, which, like light, travel at the speed of light, 300,000 kilometers per second, and they also endure. See, if you create something that could be like the perfect, the smoking gun, right? And it's the scene of a crime, as I describe in the book. If inflation's like a crime scene, you need the perpetrator to stick around long enough for the detective to show up. In our case, we needed something that could endure from the origin of time itself in the inflationary epoch, perhaps, all the way to 380,000 years. And there's only a few things that can do that. Photons have infinite life, we think. We think that protons probably do, but again, the protons were bound up with electrons only about 380,000 years later.
They came much later.
They came so much later. Yeah. And so then what you're left with are waves of gravity, and they travel at the speed of light. They endure forever, and they have just the right properties to change the structure of the CMB. And that's what we detected. We claimed we detected that imprimatur of inflation in the ultra early universe. And that's why it was so celebrated and such an important discovery.
Boy, for the first time, I finally understand that announcement.
I'm glad.
So thank you, because that was, this has been bugging me. So you're still trying to find this, right? Even
yes, absolutely.
Through similar instrumentation, correct?
Yeah. So not only am I trying to do this, my friends on the BICEP experiment have upgraded the instrument 2 more generations since BICEP 2. And you'd think it would be called BICEP 4. We actually had BICEP 3, and that's been observing for several years. And now we have the BICEP Array, which is the 4th generation in the BICEP series. And these are very simple telescopes. I showed you last time a refracting telescope is just a lens in front of a detector. With Galileo, it was a lens, 2 lenses, and then his eyeball was a detector. Right. In the case of BICEP and its successors to it, we have a microwave detection system, which is called a superconducting transition edge sensor bolometer. And I describe exactly what all those words mean in my book, Losing the Nobel Prize. And the optics that it's coupled to are just microwave lenses that are transparent or can refract microwaves from the Big Bang. We put it at the South Pole, at the very bottom of the Earth's axis. And we observe.
No, I'm sorry. Go ahead and finish.
So BICEP ultimately was brought low. Spoiler alert. My book is called "Losing the Nobel Prize." If we had been successful, it's arguable that you could argue about whether or not who would have won it, would I have won, but there's no doubt that some members of our team would have won the Nobel Prize for this discovery. It was called the greatest discovery of all time by eminent scientists at the time.
It would,
and not only it would not only be for the experimentalists, but for the theorists who conceived of it. The inflationary universe. It was a detection of gravitational waves a year and a half before LIGO announced it. So these are
yes, but to be clear, you're not actually detecting gravitational waves themselves. You are looking at their effects on the microwave, the CMB, at a resolution that it seems to me like would be much greater than what Planck could do. Planck is currently our most high-resolution map of the CMB, if I understand that correctly. So,
well, there actually are much higher resolution instruments, but I'll just point out, you're making an important point. There's a distinction between a direct detection, when a gravitational wave comes into your laboratory and shakes up this bottle of vodka. I'll take a sip. Then you can actually detect that motion via seismic shifts in the detector, in the mirrors and the interferometer. What we were detecting would be indirect evidence that gravitational waves existed 400,000 years after the Big Bang on a cosmic scale. It means in that direction over there, which is 46 billion light years away from us, and in that direction over there, which is 46 billion light years away from it, they're identical, even though they're 93 billion light years away from each other. They had the same property. The only things that could do that are gravitational waves. And I'll point out, in 1993, indirect detection of gravitational waves from the so-called binary pulsar did win the Nobel Prize. And in fact, that was the inspiration for why I was so obsessed with the Nobel Prize at an early stage of my graduate career, because I started graduate school at Brown in 1993 when Russell Hulse and Joe Taylor set out to measure and did win the Nobel Prize in physics for the discovery of gravitational radiation indirectly. And Russell Hulse was a graduate student when he made that discovery.
Yeah.
So I thought, if he can do it, maybe I can do it, and go back farther in time to the Big Bang.
Yeah, this is amazing work, and the only discovery I could think of that might be more amazing would be actual life somewhere else.
Yeah, that's right.
That would rival this.
Yeah, the eerie
So
silence.
okay, I
Right?
just want to make a comment, and then I want to read some of your comments and questions for Brian to answer. But
Yeah.
so it's going back to what you said about Einstein and the blunder and adding his cosmological constant. I mean, it was when we found out that the universe was expanding. I don't think cosmologists at the time were very happy. Certainly, this idea that there was a time of t equals 0 or a big bang, all of this stuff was really upsetting to a lot of people. They would much have preferred the universe to always have existed than to have this actual beginning, because it really was problematic, especially from a philosophical and religious viewpoint. Nobody wanted to see this. This was not a happy occurrence. But nonetheless, you can't ignore the data. It's there. Now, at no point, Brian, in your talking about all of what was happening in the very first few moments of the universe, did you say anything about a singularity? It used to be, and this is a misconception I've had until very recently, that we always ran the universe back to a point in time that had infinite density, like you said, and zero volume, and a singularity, something physics doesn't like. But we're not talking about that anymore. Now we're talking about a period where matter began, may or may not have been t equals 0. We don't know. Probably could have still been time there. Probably was. I don't know. Intuitively, I would think there is still time ticking somewhere. And then we had an inflationary period that was super amazing and quite extraordinary as far as our own experience goes. Again, this is not a singularity. This is not a point. Now, I want to make this distinction because my wife and I were talking about this 2 nights ago when I told her I was going to be having you on. And she's a philosopher, and she's been learning about the Big Bang. And she is also she studied Catholicism and very in theology. So I really trust what she has to say about these topics. And she says, this is a real problem. This idea that there was a inflation before there was a Big Bang. If the Big Bang is defined as the creation of matter, then this is a problem for religion, because especially many of the more evangelical ones are pointing to this as a t equals 0 moment, a moment of creation where easily a religious person could say God stepped in. And I think this might have been one of the impetuses of what Stephen Hawking said when he said we don't need God anymore to show the beginning of the universe. And I just want to I want to just point that out because we're no longer talking about, at least it seems to me, a t equals 0 moment of creation. As you said before, other cosmologists have said this could have been a cyclical thing. This could have come from another universe that started and gave us the initial conditions to just continue on. T equals 0 may not even exist in these ideas. So
you're saying so many interesting things. Each one of these topics could be a complete conversation, and I'd be happy to do that. I'll say a couple things. So you've heard of Robert Jastrow. He wrote a book called God and the Astronomers.
Yes.
Now he said something that I find slightly I wouldn't say disingenuous, but I'll say I don't agree with it. He said when the CMB was discovered, meaning that there was this hot origin of matter, at least. And back then, it was sort of colloquial to say it was the origin of the universe, the origin of time, but nevertheless, he said that it was as if there had been a band of astronomers, and they had been scaling this mountaintop. And when they got to the top, they saw a bunch of theologians already celebrating and self-satisfied. It's the last page of the book. And I find that actually incorrect, because it's not that the Bible is a science book. I'm Jewish. I point that out in the book, and how the Old Testament has very interesting things to say about many things, but it's clearly not a science book. And the one way you can tell that is if I give you this book, here, I'll just, because it's next to me, or my book is too far away from me to read. There's Paul's book called The Eerie Silence. You look at it and you pick it up, and there's 300 pages in it. And if there's one page in it about extraterrestrials and the rest is about the Brett Kavanaugh trial or something, you say this book is not accurate. It has nothing to do with that. It's one page, okay, but 300 other pages. Well, if you look at the Torah, the Old Testament, whatever you want to call it, the Bible, there's 35 sentences that could plausibly be related to, the origin of the universe. I mean, look, the sun is created on the fourth day. What does that even mean, day? So
Right.
I don't think it's proper for Jastrow to say that the Torah, the Bible, the Old Testament, which I have no problems with and support and find very appealing as my philosophical side, has anything to do with it any more than this book would be if it were about the Kavanaugh trial and had a different title.
That's
so
right.
I want to be very careful when we talk about, proving the existence of God or proving that, as Hawking said, that we don't need God. I think those are sophistic. I think that thinking in those terms is you're using something outside its domain, outside its magisteria, as Stephen Jay Gould said religion and science are, as compatible as, zoology and stamp collect. They're two different areas of expertise. And because you have subject matter expertise in one, as Stephen Hawking does in physics, or did, God rest his soul, if he believes in God. He's almost 2 years since he died. I can't believe it. But getting back to that subject, he didn't have any knowledge, his knowledge of philosophy, so he used to say that asking what happened before the beginning of our universe, before the Big Bang, was as nonsensical as asking what's north of the North Pole.
Right.
But that actually is not a nonsensical question, because now there are many models that suggest you can answer potentially the question of what happened on the Tuesday before the Big Bang.
Right.
That, when people ask me, what's the one question you want to know the answer to? That's it. What happened on the Tuesday before the Big Bang? Nothing or something.
Right. And I want to point out that I told you that story because I want to emphasize that none of this has affected my wife's faith in God. And if anything, she reconciles her faith in God in much the same way on what you just said. She knows the Bible, what it's a book about, and she also knows about her beliefs in God and her theology. What she was contesting was a branch of religion that uses the Big Bang as some kind of support for their theological showing that God must exist, because there was a beginning. And a beginning does have a lot of connotations to it. And science, if it can't answer that beginning, then of course that leaves open a lot of interpretations from theology or whatever. If it's outside the realm of science, fine. If science can't answer it, then science can't answer it. But it looks like we're getting to a point where we are able to say some things about this moment in history or in our evolution that are pertinent to this question. And
absolutely,
that's why I wanted to talk about it, because I didn't know a lot. I'm thinking singularities and singularities. What I've always heard and what I believe in my heart is that if you've got singularities in your theory, you've got a problem with your theory, because they shouldn't be there. So we got to get rid of them because they don't, well, what happens there? Well, no, I don't know. Physics doesn't work. Well, that's just not an answer. So, this idea of a singularity having gone away, I used to just go, well, all right, maybe it was God. Who can say otherwise? Certainly it's not science. But that's not true anymore. And
I think, and that's what makes it so delightful to do what I get paid to do, and to think about these questions and discuss them with people like you. Look, what's another example of a singularity that you and your listeners have probably heard about in physics, in black holes. Okay, so Tony, next time you have an expert on about black holes, ask him or her, what's at the center of a black hole? What's there? What's it made of?
Yeah.
You sent in all this. It's a singularity. You don't know. So how come we say, and they're comfortable saying that. So why not say we don't know what a singularity is in the cosmological context? Because I think there's, and again, I'm not proselytizing at all. I could care less if people believe, don't believe. I call myself a devout agnostic. What is an agnostic? Someone who he or she is questing scientifically, perhaps, to know the answer, but not presupposing that he or she knows the answer.
Right.
Now,
It's an open question.
Why are people more comfortable to say, I don't know, Tony, when it comes to this, what's at the center of a black hole, than what's at the center of the beginning of the universe? Because that is connected philosophically, theologically, to perhaps the existence. And again, I don't necessarily believe one way or motivate one way or another, but it's uncomfortable to say I don't know, when the possibility, if you're atheist, could be it could have been from a deity of some kind or another.
Yeah.
So I think that's what makes my life so enjoyable, is that we're actually building instruments to perhaps answer that question. Because if we succeed, in a sense, we don't ever like to say we succeeded in looking what we found, because that's confirmation bias susceptibility. But if we do find that it's not possible to have a cyclic universe, that would have tremendous implications for some of these very questions that you're asking.
Are we ever going to have any hope? This is why, I mean, I bash on string theory all day long, because I think it's just not even science. But are we ever going to be able to verify any of this? stuff.
Very interesting. So what I just said a second ago actually has pertinence to what you just asked, because I said we won't be able to prove, inflation occurred, but we could rule out its chief alternative, which is a cyclic cosmology, or as Roger Penrose calls it, this conformal cosmology, this aeon cosmology. We can actually rule those out. So that's what's called falsifying a theory.
Yeah.
When you can prove a theory is wrong using data, that doesn't prove what is true, it proves what is not true.
That's true.
And that's as close as you can get to truth in physics. Now, you're asking a question, can we prove that string theory, or can we find evidence that string theory is correct? The answer is
not
no.
string theory, because we can't.
Yeah.
But I'm talking about this inflation,
Right.
inflationary idea.
So I think the best hope that we have is to either exclude all the other possibilities, find evidence that inflation is wrong, or say simply that we'll never have, it'll be forever hidden behind sort of a firewall by this existence that is commensurate with a singularity. And we don't know now. We're going to have answers, hopefully, from the Simons Observatory, which is a project that I co-lead with 300 other people on planet Earth. A pretty exciting project. That's my next big project in the Atacama Desert, northern Chile. And
Awesome.
We hope to find answers that will tell us if we can rule out models of inflation, models of cyclic cosmology, or eon cosmology. And that, to me, is the most exciting part of what I get to do.
And so we can make statements like, if inflation didn't stop, then we wouldn't be here. If inflation went on forever, then we would see the following things. So we can make statements about, if inflation occurred in the way that we think, then we should see the following things in the CMB. And
That's
you look
right.
for those things. So, and if you,
That's right.
and then you say, and if we do see these things, then what this means is certain things didn't happen. And so
Exactly.
you can rule stuff out, narrow it down, but we're not probably ever going to get to a definitive answer on stuff that happened behind the veil of the CMB, just because of
100%.
the way our universe is structured.
Exactly correct. Exactly.
Okay.
I couldn't say it better myself.
All right. I hope that you guys are following along with this and that you got something out of it. God knows I did. This was awesome. And I want to go with just a couple questions, because I know, Brian, you got to go. But there's a couple here that I want to, that I hope I can find. Oh boy, darn it. Oh shoot. Here's one from, Yuriko Roberto. This is from, I wanted to ask this. How is it possible that 2 points in space time can expand or move away from each other at a rate that is faster than the speed of light?
So the only, I could say to you, well, they're faster than the speed of bread. And you can say, well, what does that mean? What is the speed of bread? There's some limit at which something cannot travel faster than this value. And it happens to be that what we say is information cannot be propagated, according to Einstein's theory of special relativity, faster than the speed of light. But that says nothing about the separation of space-time itself. It just says that you cannot send a signal between two places in space that travels faster than the speed of light. Okay. So there's nothing forbidden about the actual space-time itself expanding at any given moment, perhaps faster than the speed of light. In fact, there are regions that we see quasars, say, at a redshift greater than 1. That means they're receding faster from us than the speed of light. And we can get into how it's possible to see them. We see, as you pointed out, we see quasars and objects, as you pointed out, redshift 7 almost, redshift even more than 7. That means 7, formally speaking, it means about 7 times faster than the speed of light, yet we can still see them. The CMB surface is expanding 1,000 times faster than the speed of light, but we can never reach it. We can never send a laser beam to it and say, we are here. In fact, anything outside of what's called this particle horizon, we can't communicate with.
Well, I got really bad news, and that is that you can pretty much stop your work, because Neil, you just won the Nobel Prize. Here it is. Here's the answer to everything. Okay. Is the speed of light limit just the limiter of the AWS cloud server plan our sim is running in? There it is.
There's another question. Okay,
that's right. So we can stop looking for all this stuff. We're never going to get past it, because we can't pay Jeff Bezos enough money for enough computing cycles to have a better simulation.
That's the Prime directive. Yeah. Amazon Prime directive.
All right. Well, I guess we better stop. It's after 4. Brian, this was a lot of fun, man. Thank you. It
was, and I love talking to you. I love the questions in the chat. I'll try to answer them if I have time. Remember to sign up for my YouTube channel, just Dr. Brian Keating. I'll put a link in the chat right now. Maybe Tony, you could pin that to there too.
Yeah.
And then sign up if you live in the U.S. Again, I'd love to send you a meteorite. Here they are. They're magnetic because they're made of star stuff. They're made of the core of a Type 2 supernova that, fortunately for us, didn't detonate too close to home, but just close enough to form the material in our Earth's core and us and the hemoglobin in our blood. So sign up for the mailing list. If even if you're not, sign up as well. And if you're in the U.S., I'll send you one of these.
Do you live stream your podcast recordings?
They're all on YouTube. I don't usually do live chat because it's a little difficult to set up.
Tell me about it. I know questions. It's like paying attention to everything at once is a real
I like to just go deep and talk to the authors or the spacewalkers, as the case may be. Yeah, check out the channel and be in touch as well. I love talking to your viewers.
Okay, well, thank you so much. And Dr. Brian Keating with us, professor of astronomy at University of California, San Diego, working on a great many things, author of the book, Losing the Nobel Prize. Link in the description box. Please support him and his channel by either getting the book or signing up and subscribing to his newsletter and YouTube channel. So thanks again, Brian. Will you come back and let's do the talk about nothing?
Anytime, yeah. Let's do it in March. So maybe on the anniversary of the Bicep 2 announcement.
Okay, sounds good. All right. Well, thank you. All right, thank you, Brian.
Bye, everybody. Thanks for your questions. Bye, Tony.
All right, bye. All right, guys. Thank you. I guess I'm going to stop the stream now. I want to thank you all so much for watching, and I'll be back next Tuesday on T-Cube, Tony's Twitch Tuesday. Also, whoa, I just got cut up because he left the chat. I'll do that. Tony's Twitch Tuesday. And then again next Thursday, probably be just me talking about some topics that are of interest to me, most notably things, probably do some SpaceX stuff, and there's a lot of good news coming out that we want to cover during that Thursday. So I'll be back then. Man, you guys were awesome. Thanks for the great comments and questions. And little forewarning here, in about 55 minutes, watch my channel. I've got a new space video coming out on Apophis. It'll break at 5 p.m. Eastern time, so please look out for that. And I just put it up before I started this stream. All right, thank you guys so much for watching, and as always, keep looking up.